In this video, we're going to look at a force that is heavily associated with one of the forces you guys were looking at last time, which is the force of gravity. Now, it's not equal to the force of gravity, but it's often connected to it or caused by it, so we're going to work with it a little bit. Now, the force that you guys are going to look at today in this video is what's called the normal force or natural force. Now let's just start with a basic setup here to give an idea of what we're talking about here. So, I'm just going to draw the common thing to start with is like a table or something like that. So you'll draw just a couple table legs. Okay, so you got like a table. Shade that in a little bit. Okay, and on top of the table, we just need to put something on, an object, whatever it is, on top of the table. Oh, and for that, here, we're going to use a little bunny. So there's a little tiny bunny. Oh, he's too big. Let's move this down a little bit. There we go. Now we'll put the bunny on top. Here's my bunny. All right, that's a little better. Okay, so we got a bunny on a table. All right, now, obviously, the bunny is applying a force on the table, which, of course, is from gravity. And this connects to what you guys did before. So for a bunny, we have obviously there's a force of gravity in the bunny, and the force of gravity is going down. So the force of gravity equal to mg. Okay, now the bunny isn't going through the table because the table obviously is pushing back up on the bunny. So the table, of course, pushes back on the bunny, pushes up. Something like this, keeping the bunny from going through the table. And this, well, there's a couple names for it actually, but this is what's called the normal, or sometimes actually called the normal or natural force. Okay, and this is our sort of like our new force we're going to look at a little bit today. And it often comes from gravity because gravity pushes things on surface. There's sort of pressure between the object and the surface pushes back. So we have this normal natural force. And the basic idea for this force is you have some kind of force, whatever it is, you got a force. It could be the force of gravity. It could be an applied force. It could be lots of different things. Basically, a force puts pressure between two masses. And it's not a pressure measurement, but it's connected to pressure. But you have a force, in this case gravity, puts pressure between two masses. And there is, that sort of like that pressure, pressure is not the right word, but sort of like the pressure or the force between them. This is the Fn, or the normal force. I like to call it the normal force. Sometimes you'll often hear it called the natural force as well. But it's sort of like the force between two masses that are in contact with each other. So there is a normal force between the bunny and the table. So I often like to think of it, I almost like to think of it as like a contact force that's why I often like to think about it. You have to have two things in contact with each other, and that force between them, that contact, almost like pressure type idea, that is normal force. And that normal force exists between the two objects. So if you have an object by itself, there's no normal force. For example, if, here's my bunny. You take the bunny, and the bunny is not sitting on anything, but maybe the bunny is falling, something like this, and it's falling through the air. There is no normal force because it's not in contact with any other surfaces. You have to have two masses or two objects in contact with each other in order for that normal force to exist. Okay. Now, the reason why it's called the normal force is because in math, normal means perpendicular. And that's where the term comes from. So this force is always at a 90-degree angle to the surfaces. And again, my falling bunny wouldn't have one because it's not in contact with anything. Okay, so this guy over here, there's no Fn whatsoever because there's no second thing. Now, as soon as, it lands on the table or the ground or whatever, you catch in your hands, there'd be normal force between the bunny and the hands, but that's something different. Okay, so let's look at a different type of scenario. So let's say we have this here, take a ladder, okay, laterally on the floor and the wall. Every time there's contact between surfaces, there would be normal force. So there's normal force here between the floor and the legs of the ladder. There's a normal force here, or even along the entire thing where it's touching the wall. There's even like normal force in between the two parts that are folded together where they are in contact with each other. Whenever you have two things in contact with each other, two parts, you will have a normal force. Okay, and it's always perpendicular to the surface, which is where the Fn comes from. Some people call it the natural force. I sometimes call it that as well, but I usually call it the normal force. So let's even just take something really simple here, similar to that right there. Okay, so we'll just use boxes because it's easier. So we have a table or something like that. We're going to put some boxes on here. Ooh, that one's a little big. We'll make that a green box. We'll make another box, something like this. Make that one red. All right, something like that. Okay, and they're just sitting on a table. So this is just the table. All right, so let's say this one here is 8 kilograms, and this one right here is 10 kilograms. Okay, so let's do something like that. All right, so I know I'm going to, this has to do with gravity and stuff like that for this one, so I'm just going to do the mg's to get them out of the way. All right, so the mg for that one, that's really easy. That's 98 newtons, and the mg for this box is also really easy, right? We just got to do the 8 times 9.81, and the weight of that box is, now I'm just going to round off, is 78 newtons, something like that. Okay, so there's a couple places where we can find the Fn. Wherever there's contact between surfaces, that's where Fn exists. So there's no Fn on top of the red box, but there's an Fn right in here between those two, and there's an Fn right there between the green box and the table. Now, if we sort of look at what causes them, they're all caused by the force of gravity pulling down on the two boxes. And this is the reason why Fn and force of gravity are often connected to each other. So if I did the Fn on the top there, if I did this one right here, oops, if I did that one up there, that Fn would just be 98 newtons. It's just the weight of the red box pushing down on top of the green box. That's it. That's why there's pressure and normal force between those two parts right there. So for the box on the bottom, you got two boxes on it. You got between the over here, the Fn for this one, it's not just the pressure because of the green box, it's also got the red box pushing down on top of it. So the normal force between those two, between the green box and the table would be the combination of the two weights. It'd be the 98 and the 78 put together. So you get the 98 plus the 78, put the combination together, and you get about 176 newtons. And that would be the normal force right there. And obviously, if the red box was taken off, there'd be less pressure and normal force between the green box and the table, and it would just be 78. But with that 10 kilogram box on top of it, it really increases the amount of pressure and the normal force between them. So between the red box and the green box, there's a normal force of 98, and it would be pushing straight up this way, perpendicular to the surface. And for the other box, the green box, there's a normal force between the surface and that one, pushing straight up with 176, also perpendicular to the surface. So hopefully just from this you can see why gravity and Fn are often connected to each other, especially in grade 11 physics for the basic stuff that you guys will actually be doing. But it exists between any surface. If you push on a door, there's normal force between your hand and the door. There's normal forces all over the place. But for most of the stuff that you guys will be doing, that is a really common way to get the normal force is from gravity. But we'll look at other sources as well. Okay, so let's clean this up, and then I can show you another type of scenario where another really common type of scenario where normal forces kick in. And let's just take, let's just take something really simple. A couple wheels, make a big box. There we go. Let's fill in that box. There we go. Okay, just have a person. There we go. Have a person pushing on the box. There you go. Something really, really simple. and let's say this is an 85 kilogram box, and it's moving along, and let's say it's accelerating at, let's go with just 2 meters per second squared. Okay, so there's a few things going on here. And there's normal force. We're going to find normal forces that are on the box. Now, one of the most easy things is underneath the box. I mean, you've got the force of gravity is pulling the box down. So there's normal force between the wheels and the ground. If we just did the mg for the box, just do the 85 times the 9.81, the weight of the box is like 834 newtons. So that would be the Fn, and that would be the Fn that is right there. Now the thing is, what you could say, if there's 4 wheels, if you had like 4 little tiny wheels, each one of them actually has a normal force. So each one would, if you divide that by 4, there is 208 newtons of normal force for each of the 4 wheels. So the total normal force between the box and the ground would be 834, divided between the 4 wheels would be 208 for each one. Another really common place for normal force on this box is another place where there's contact between surfaces, and that would be right here. And of course, the guy is pushing on the box. So there's normal force between his hands and the box. And of course, him pushing is causing the F equals ma, it's causing the box to accelerate. And if you did like the basic F equals ma, you get the 85 times the 2 meters per second squared, there's 170 newtons of force. And that is coming from the guy pushing on the box. In fact, that would be the Fn right here. The Fn would be 170 newtons between his hands and the box. And of course, you could cut that off, cut it in half, and you could split it between the hands if you wanted to, but the total Fn between the guy and the box is 170 newtons, and that's what causes the box to actually move. So this is just a very simple illustration of Fn, and often Fn will just be equal to the force of gravity, but sometimes it isn't. Sometimes it comes from something else. Okay, but let's show you why this connection really kicks in. One of the biggest things that Fn then relates to or is connected to. Now, where Fn really comes into play a lot has to do with friction. Okay, and the force of friction. It is a very, very, very common force used to slow things down, and that's what it does. Is it's a force that actually prevents motion or slows motion, that type of stuff. Now, of course, some people go, well, hey, wait a minute, friction is what I use to walk. Like there's friction between the ground and my shoe. And that's true, but it still prevents motion. When you push back on your shoe actually wants to slide backwards, but friction prevents it from sliding backwards, which then causes you to move forward. So there's different ways you can look at it, but it's basically a force that prevents motion and slows things down. Now, where does friction actually come from in the first place? Well, it always exists, between different surfaces. You have to have it between surfaces, and hopefully already you can see this is going to connect to Fn because we're talking about forces between surfaces, and Fn only exists between surfaces. And if you take, it doesn't matter what kind of material you look at, if you magnify a material or surfaces, if you zoom in far enough, they eventually all look bumpy. No matter how smooth they appear, if you magnify it far enough, everything's got bumps and grooves and that type of stuff in it. Even something that's super, super smooth, you magnify far enough, it's going to look bumpy. Now, it's sort of, you've got these little, it's almost like there's like tiny, they're not really teeth, but they're sort of like tiny little teeth or bumps, whatever you want to call it. These sort of like lock together, or they sort of prevent motion. So you got these little tiny teeth. They sort of lock together. When these two things come together, the little teeth and the grooves, they sort of interlock, and it's really hard for the thing to go sideways, and they prevent the motion. That's where friction comes from. So there's a couple things that actually dictate how much friction there actually is between materials. Now, one of the things that it depends on the materials. It depends on which material. Some materials are a lot, not stickier isn't the right word, but some materials are a lot harder to slide across than others. And that actually has a lot to do with the nature of the little tiny teeth and the bumps. And this is what's called the coefficient of friction. And every type of combination of materials you have can have a really higher, lower, regular type of coefficient of friction. So something like rubber feet, like on the bottom of like a lot of furniture and things on shelves, sliding them can be tough because there's a really high coefficient of friction, where other things will have really low coefficient. They slide really easily. They have really high or low coefficients of friction. It all depends on the combinations of materials and how well they can actually slide. Now, the other thing that it depends on, so one was depends on the materials, but also depends on the actual amount of force. Causing, actually, I'm going to erase that. It's actually the force, not causing. It's the force. Oops, wrong tool. There you go. Force between the materials, and this is the Fn. Because if you've got a huge force pushing those materials together, these teeth can really, really lock together tight. They go really far in, they can really lock together. But there's only like a little bit of pressure, a little bit of force holding them together. They can still move and slide relatively easily. So those are the two things that friction depends on. Hopefully now you can see why Fn is really important for this type of thing. We can really lock those things together. So friction depends on the nature of materials that actually exist, and how well or how big the teeth are, how they interlock, how flexible they are, how rigid. It really depends on the combination of materials. It's not just one material, it's always a combination of two materials. Like there's no coefficient of friction for rubber, but there is a coefficient of friction for rubber and concrete, rubber and glass, rubber and cement, whatever you want. It does whatever surface you want, linoleum, it doesn't make any difference. It's always the combination of the two materials together. And then also depends on the amount of pressure or force pushing those two surfaces together. And that Fn can come from lots of different things. And it is often from the force of gravity for us, because often we're trying to push things along a flat surface, like boxes, furniture, whatever you want, and it's the force of gravity pushing it down into the floor, the tabletop, whatever you want, which is then Fn equal to Fg. But it can come from other things as well, but it is often the force of gravity. So that's why we sort of look at the force of gravity a little bit, and then we can also then eventually connect it to friction. So when you actually look at it, if you actually want to calculate the force of friction is then connected to these two things. The coefficient of friction, the symbol for that is the Greek letter mu. It's like a U with a long tail in the front. It's also the symbol for micro. And that's the symbol for the coefficient of friction. And then Fn is just at the end, something like that. So we've got the friction can be calculated as mu Fn. And then once we know that, you typically find the Fn from wherever it's from, connect that to the coefficient of friction, and then you can then find the force of friction, which you can then apply to the situation. Okay, so that's the idea behind Fn, which is really, really common force between all materials are in contact with each other, and eventually Fn is then directly connected to friction, especially for what you guys do with basic dynamics, because it is one of the main factors that dictates how much friction there is between materials. Okay, so we'll do a little more practice with things like Fn and then connect it to friction as well as we keep on moving with your basic dynamics type stuff.